Let's actually go through an experiment to show that it happens, and also this way I can show you the manipulate function in RStudio. So we're going to use RStudio's manipulate function to find the value of mu that minimizes the sum of the squared deviations. Okay, I wanted to go through this slide, but I actually wanted to execute the code. Just to remind you, all of the lecture notes in this class are on GitHub as part of our data science track, so it's all perfectly reproducible. And all the code for everything, whether it's included in the slide or not, is actually embedded in this file index.rmd. R stands for R Markdown. It's an R Markdown document. So here's like these three little slashes say to display the code. Let's actually illustrate. I'm going to use the manipulate function. So I'm going to do library manipulate, and then I created my own histogram function here, and there you go. You can go through the code, and basically all that does is create a histogram function to go into manipulate, and then the histogram function only depends on this one variable mu, which is where it puts the line where it's estimating the mean to be at. So here's my manipulate function. Now, so focus over here, okay? And here you can see the value of mu that it's currently at, and then that the mean squared error. In this case, I took the mean squared error. I took the average squared error rather than the sum of the squared errors. But obviously, if you minimize the mean squared error, you minimize the sum of the squared errors. So okay, so now we can move this slider along and see how, as we change our mean here in this case to 64.5, how we decrease the mean squared error. And what we want to do is find the point where we can put this red line that minimizes the sum of the squared errors, or the mean squared error in this case, what I'm displaying. And as you can see, you know, it's going to be somewhere right around here, right? Let's see. Oh, it looks like right there. It looks like around 68. Or so, but let's actually figure out what it is. Of course, you can always just do mean Galton star child, and I'll give it to you exactly. It's 68.08. But anyway, this just shows you what least squares is doing. It's sort of moving around that red line and finding the exact optimal place that will balance out this histogram as if you were putting your finger underneath it. Okay, so just to remind us, the least squares mean works out to be the empirical mean. Here I show you exactly where it is and how you can just draw where the mean is on the histogram itself. And then let's actually just go through the math as to prove that the least squares mean has to be the empirical mean. We don't just have to do it with, or we don't have to just do it experimentally by using manipulate. We can actually figure this out. So let's start with our least squares mean criteria. And again, if you want to skip some of these details, I'm providing them just for the people that are interested. If you want to take the class where you skip over a lot of these kind of intricate mathematical equations, then don't worry about it. That's perfectly fine. The quiz questions won't focus on the mathematics. But if you're interested in the mathematics, I do all the mathematics in such a way that you don't require either calculus or linear algebra. So all you need to know is basically how you can, if you can do a little bit of symbolic algebra and summation notation, you should be fine. Okay, here's the least squares criteria. Let's add and subtract y bar, okay? And then let's go to this next line. If we were to take this guy and square it out, we'd wind up with yi minus y bar squared part. We'd wind up with a 2 times this cross product part, and then we'd end up with a y bar minus mu part. Okay, this part right here, right, the y bar minus mu part doesn't depend on I, so we can pull it out of the sum to right there. And if we move this sum inside the parentheses, right, y bar doesn't depend on I, so it works out to be ny bar if we add it up n times, and we have summation yi. Okay, so summation yi, just remember we define y bar as summation I equal 1 to n yi over n. So of course summation yi is equal to ny bar, so this whole thing is 0. Get rid of that. And then you wind up with this guy right here, plus this extra term right here. But notice all of these terms are positive because they're a bunch of squared things. So we're adding up a bunch of squared things, so it's positive. So, right, so if we get rid of it, we can only get smaller, right? If we have a number and we take away a positive thing, then it can only get smaller. So we create that we have to get smaller when we get rid of that, and we get this guy. So okay, so just to recap, for any arbitrary mu, the least squares criteria, the least squares equation, is larger than if we plug in mu equal y bar. So that must mean y bar minimizes that equation. So it's interesting that you can show this very easily without any calculus or anything like that.